How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at electron configurations and the periodic table. So our objectives will be to analyze the structure of the periodic table in reference to the electron configurations of its elements. So let's start looking for patterns, right? The whole periodic table is all about organizing things by patterns. And you notice there's a weird shape to it, right? You got this kind of like a step down, going across, step up, and then they're not even symmetrical. And then you got this thing going on over there, and you don't know what that's all about. But let's see if we can make some sense of this weird shape. So let's start by talking about how many electrons can fit in the following sublevels. Well, we know S has one orbital, so it can fit 2 electrons. P has 3 orbitals, so it could fit 6 electrons. D has 5 orbitals, so it could fit 10. And F has 7, so it can fit 14 electrons. Well, let's see. Do we see a pattern like this at all in the periodic table? Well, hey, wait a minute. This tall set over there is 2 electrons. This kind of shorter set over here is 6. And then, wait, if I count all of these transition metals, there's 10 of them. And if I take a look at how much or how many different elements are there, wouldn't you know it? There's 14. What's with this pattern? Well, that's it, right? So that tall block that's too wide, we call the S block because it's filling in S orbital electrons. Over on the other side, the 6 wide block, we call the P block because that's where the electrons are going, into the P orbital. The middle block we call the D block because there's electrons going into the D sublevel, and then that separate thing we call the F block because electrons are going into the F sublevels. So let's talk about filling it in. How's this like also reflect the diagonal rule? So we start 1s2, so we start in that first period and we do the 2 electrons 1 2. Right, next we fill in the 2s sublevel, right, and that's what we're seeing right here. Well, after that, we got to jump across this large gap, and we start into the P block. So we're into the 2p electrons, which still jives with what we know about the diagonal rule. And then third period, we start with the 3s. There's 2 electrons there. We jump across the gap to go into the 3p. And now, oh, hey, look at that. Following the diagonal rule, after the 3p, we go into the 4s. All right, and then following the diagonal rule, after the 4s should come the 3d electrons, and that's what you start to see. And again, you continue on, it's following this diagonal rule pattern, and then what happens once we get to these lanthanides? Well, it's the same thing. After 6s, now we're jumping back to the 4f, right? So if I kept doing this diagonal stuff, and I'm missing some stuff, but I'm going to go 4f. And then, well, after that, I'm going to go into the 5D. And that's what's shown there in the D block. And then after that, I'm going to go on to the 6P. And then so on and so forth. And you start to see this pattern. And you can kind of look at where an element is on the periodic table and figure out what its electron configuration should be. Piece of pie, right? Now you see that pattern. Oh my goodness. Piece of cake or pie, whichever you prefer. But, of course, there's exceptions, right? It can't be too simple. So why are there exceptions, though? Well, we know that principal energy levels start to overlap. And the energies for the 3d orbitals and the 4s orbitals are really close in energy. So sometimes having half-filled orbitals is going to be better than filled orbitals. And I'll show you what I mean. So, for example, chromium. If we're looking at chromium, what you would expect following the pattern is to be, argon, and then 4s would be the next box, and you'd have up, down, and then you'd get into the 3D, right? And the 3D has these 5 boxes, and I can't draw for my life. So you go, all right, well, I know I have to add more electrons. So you go, all right, I would expect there to be 4 more electrons in the D. But what actually happens is this electron from the 4s goes, hey, wait a minute. These orbitals over there are almost the same energy, and right now you got me paired up with another electron, which I don't like. I like to be repelled. I want my own orbital. So it's going to move and actually end up into the 5d orbital. So what you actually end up seeing is this, because having half-filled orbitals and having them unpaired is lower energy than actually having them in the appropriate orbital. You also see this exception with copper for like the same kind of reason. You fill up the D sublevel this time and you leave the S unpaired. So yeah, other exceptions include in the lanthanides series for a similar reason. The 4F and the 5D orbitals are very close in energies. So again, you see the same kind of discrepancy. You would expect one thing, but it ends up being something else, right? So there's a couple other exceptions, but what you really need to know is that there are exceptions, but the general pattern is still very useful. So yeah, summarize. Can you analyze the structure of the periodic table in reference to the electron configuration of its elements? I hope so. Okay, bye.